Cool. If you remember, the way we began the lectures of the No, what have I done? I've killed it. I've probably killed it. So, not touching anything. Good lecture. Good lesson. Oh no, it's there. Let's not talk about it, because otherwise it will feel our fear and stop working on it. Okay, now if you remember, last period, when we began the course, I started with a question. And the question was, what is this? It's a number, it's an integer, it's a piece of information, right? It's a number. What sort of number is it? 3. And I agree with all of these things. We're characterizing what a number is, and we all agree. There's plenty of ways to describe a number. What's its relevance for us?
We don't know without context.
We don't know without context. How do we provide context? By binding it to another piece of information. And what is the other piece of information? Yes, so another piece of information, I'll follow your example through. Age, I bind the two together, but whereas on the right, we can have very, very many different structures of information. To the left, we only have one sort. What is to the left of a binding? It's a name. If we change it, then it varies, then it becomes a variable. But for the moment, it's a name. So we bind a name to a value. Now, a value can be plenty of things, but actually to an expression. And to the right, we can have numbers, floating point numbers, strings. We can have objects themselves. But now we know that this 3, it's, 3 is kind of in the air. There's this metaphysical place of ideas where numbers exist, and there's this metaphysical 3, But now we're pointing at it with a human finger and saying the age is 3, And that's a way of pointing at it, because age points at 3. So okay, 3 is never going to change. 3 is always going to stay 3, Long after we're dead, 3 is going to stay 3. But the age changes, so the information gets bound to some other piece of information. So age will become 4, 5, 6, etc. Now, of course, if you change the context, then the value, the meaning of this value changes dramatically. So if we say debt in euros is 3, well, okay, so he owes you a coffee, okay? Kind of a slightly expensive coffee, but it's fine, right? But suppose I said debt in billions, and there's 3, then now you're Germany and he's Greece. Shit, and now I can't put this on YouTube anymore. Right? But so now it's changing a lot. So the meaning of the information is actually changing completely. But 3 is always the same, right? So 3 is 3. It doesn't change. Then maybe you pay €1 back to him. Just 1, And now the debt becomes 2, but 3 is 3, right? Okay, cool. So, what is the action we just performed with such dramatic results on our understanding of what's happening? So we had 3, it meant nothing, okay? Purely abstract concept. But how did we give meaning to it? By naming it, by binding it to a name. Names are the fundamental way in which we express meaning. Nice.
let's define another name. I'm actually stepping out of programming language. I'm going back to our meta language. This is not Python anymore. I say car is car. No. Okay, so car. And let's go for the luxury car. So let's say brand is Renault, and model, I said luxury, so it's going to be the glorious, undying Clio, and the year is 1991. Yes, but it has a full tank. Yes, so 100%. Okay, and let's also say it moves linearly, so you can only use it to go to the end of the of the garden and then back. So the position it's at the house, so 0, and when it's at the end of the garden and it's 100, then it comes back, or you push it back. Okay. Now, all the things we're giving names to right now, or if you wanted, the restriction on taking notes is lifted. If you want to stop taking notes, you might stop. If you want. It's not a good idea, but you may stop. Now, okay, so we said that core has this is bound to this block of information. We said that the depth in billions was 3, etc. So we're giving names to things, right? These are things. 3 is a thing, you know. That car, the part of the right, the part to the right. So brand is Renault, model is Clio, etc. You will agree this is a thing, right? And what for name we give it? We call it car. It's not a very imaginative name, but it's still a reasonable name. Okay? So we've given names to things. And we can represent these things with values. So there is a relation. We have the real world with humans, where humans live. In this real world, we have a car. Yes, this car has it has a full tank, right? And in the world of computers, so you don't forget, yes? And in the world of computers, well, we could translate this, and the process of translation is done with our imagination and understanding. This becomes a state. So this becomes the brand is Renault, etc. Okay? Just gonna put dots here. So the things we put above, okay? But in the real world, what can we do with such a car? It exists. We've stated it exists. We can drive it. What else can we do with it? If it doesn't start, what should we do? Oh, we can push it. Come on. Come on. For example, we can turn it on, we can turn it off, we can open the door, we can close the door, we can fill the tank. We can do all these things. And what are these these things I'm mentioning? What are they? They are actions. Yeah, actions, right? And what is the effect of an action such as drive? Okay. So let's say it has only one direction, you know? It can only go back and forth, so the steering wheel is broken. Okay? But so we can drive it. I'm going to draw an arrow because actions, you know, it makes sense to draw them as arrows instead of pictures because the arrow changes stuff. It's a process, and the arrow, you know, boom, you shoot it and it moves. You know, the arrow represents movement in our imagination. And let's say drive. And what are the things that are going to happen? So the car is presumably going to roughly retain its physical shape, roughly. But what happens when we drive it? Sorry? Yeah, but we have no wheels here. Look here. Look, so this is what we're modeling about the car. So the position changes, yes, and the fuel goes down, right? So the position. Okay, suppose that the car was here, and now the car is further along the way, and the tank is now empty. Okay. Okay. Now these cars they don't burn too much fuel. So okay. And so, but this car also has horrible arrow. But this car also has a representation in the computer. So it will be the same representation, but here originally we had that the fuel was 100, and now what do we expect? Sorry? 80. Now it looks more like the half. So it's 50. Okay? And now the question is, okay, so I have an action of driving the car in real life. But which arrow is, where are we missing an arrow? Yes? Between the states. And we're missing the translation of the concept of driving in the computer itself. And so this arrow here, I'm going to draw it dotted, because yeah, it doesn't exist yet. Very interesting. Very interesting. So we can translate stuff, we can translate things into memory, but we'd like to translate actions into memory. Into memory in the computer world. How will we build such an action, first of all? Sorry? What's a function? So that's the equivalent of are we there yet? No. The things that we know already, we cannot build the concept of functions with the concept of functions. We'll see recursion later, but not today.
Maybe instead of giving a specific value to the variables, put it in a variable, and then you can change it to form an action. Instead of
okay, but how do I form the action? What is the action? What does the action do? In that arrow, the missing arrow, the right arrow,
it changes the
state. It changes the state. What is the only thing that can change the state that we have seen?
Expressions.
Almost? Above expressions?
The variables.
No, the variables are the state. We want to change them. Evaluating what? What do we evaluate?
Program.
Not instructions. Not expressions. Instructions. Instructions are the fundamental component of actions. So this translation here will be made up of instructions. So we agree that we have here states, objects in real life, and these objects are mapped into let's not go shopping. So an object is mapped, if you look here, to what? To a state. Yes, to state or memory. Okay? And then we have actions. And actions are mapped to instructions. Yes, so a bag of instructions. And actually, the actions transform objects back into objects. Okay? And this circular arrow I've been drawing, this is just the flow of time in real life, whereas this is the eval mechanism that we define. So it's the computer, it's the flow of time within the computer, right? Cool. But my question is, okay, if you look at this, then now is drive an instruction? How many things is drive supposed to do? How many things is it going to change? 2, position and fuel. Okay? It changes two things. And we know how to change things. It will be something like fuel is fuel minus 50, and position is position plus 50. Okay? Okay. So like I will actually state this, that drive has to be something that changes the position. So position is position plus 50, and fuel is fuel minus 50, right? And now I will put some decorators around it, because now otherwise it's not very clear. So we're defining kind of a new instruction, you know, and I want to delimit it clearly. So I'm going to put angle brackets. I'm going to say, okay, the definition of drive begins here and ends here. I'm also going to put something. We're going to see through this in a moment, but for the moment, bear with me. I'm also going to say, okay, and we also put brackets and an arrow. So what I'm stating now is that drive is two instructions, right? I'm putting them together, and I'm saying these two instructions, after each other, I call them drive. Why? Well, because drive is much easier to remember than reduce the fuel by 50 and increase the position by 50. It's a mouthful. Whereas if I say drive, and we agree drive means that, it takes far less time to express this concept. Just a minor note. This transformation I've defined between the domain of reality and the domain of the computer is called a homomorphism. We'll get there in 3 years at least. But for the moment, I'll just drop the name here. Homomorphism. And this means that it's a morphism means transformation, and homo means same. So it's a transformation that keeps the same structure. Because you do expect that if we're modeling a real life system in which the car drives, and after it drives, the fuel is half of the fuel that we have, then we want that whatever happens on the right-hand side to behave in the same way, right? So we say fuel 50 because to the left in the real world, we have half a tank of fuel. Okay? Everything you do as programmers is a homomorphism with respect to some real domain that you're trying to model. But back to our definitions. Now, we've seen it for drive. I want to do something much simpler. I want to do the very same, but on a tiny example. I'm going to say that increment x is also one of these brand new instructions. And what do you think incr x is supposed to do? Sorry? Okay, so more details? X becomes x plus 1. Look what's happened. Did we agree on this before the lecture? No. So you just knew it. How? Yes? And why? Yes, but by just giving the name, he knew the implementation. But if I said, okay, Jim is, then would have no idea what I'm going. But I said incr x. And so what is incr x going to do? It might increment x. Yes? So the right name, we didn't even need to put the implementation. So actually, we put the implementation once, but now we just remember incr x. So you see the power. What's happened is magical. He read my mind. Or actually, I set up a program so that he could read my mind. So we're touching metaphysical points here. Now, x is 0 here. What do you think the state is going to be at this point? I draw a dotted line here. What is the state going to be? What is x? So I hear 1. I hear infinite. That's very trippy.
X is still 0 because you didn't use increment.
X is still 0! Because I'm not saying increment x, I'm just defining what incrementing x means. Just because we said what drive means, you know, you have a car, and you know what drive means, it's just gonna drive. So you put it, you park it in the garage, and now it just drives, you know. You leave, you go home, and the car drives. Why? Because it's supposed to drive. No, you have to initiate an action. You understand? So I'm saying, okay, x is 0, and I'm also saying what x means. I'm not saying increment it. I'm saying this is what it means. Later on, maybe it will happen. Who knows? Who knows? It might not. So now, in the state, what we're also going to find is that x is, what do you think we're going to find in the state? Almost. The whole function. The whole expression. So the whole thing we assign to x. Like, look, we assigned as 0 to x. What do we find in the state? 0 bound to x. What are we going to find? What are we going to find for x? Kind of the same principle, right? So what we assigned to x. That's unit goes into x is x plus 1. You know, we keep it simple. We keep it simple. If there is no reason to make it complex, you know, life is difficult enough. You know, we try, you know, the principle of least change, the principle of least pain. You know, to keep life bearable. Yes. Okay. So that's the only thing we find. Cool. So now we have defined an action. We keep the action in the state because somewhere we need to have it. And now we can invoke it. We can call it. We can activate it. It's an action, so we activate it. Action. Activate. There might be a connection there. And how do we activate it? Well, how can I tell you to drive?
Well, talk to me and tell it.
Drive. Right? So how do I tell the machine to increment x?
Increment x.
Look. Increment x. Would be kind of cool if in a programming language you put an exclamation mark. We don't. We just put brackets. Still, kind of makes sense. It's really cool stuff, but we'll see that the brackets also have a function. Also have a function, have a meaning. Now, a little bit about terminology, because otherwise we don't understand each other. Now, this here we call a lambda expression. It's a beautiful moment for you because it's your first Greek letter. Lambda looks like this. You're too young to have played Half-Life. It's a pity. You should. But anyway, that's a lambda expression. But in the state, when we bind... Oh, and sorry. This here is the body of the lambda expression. And the binding in the state of a lambda expression and its name is what we call a function. That's the point where you say, oh, let's do this again. Wait a second. That's the point where you say a function. Okay. Okay. Now, and the question is, when we run the function now, what's going to happen? Now, this general pattern would look like eval, and in eval, we have the name of a function, like incr(x), then the brackets, for the moment empty, and then a state. But if you look at the example of incr(x) that we just put, what do we expect is going to happen here to x? X becomes 1 by virtue of what? And incr(x), does it change? No, the action doesn't change. Executing an action does not change the nature of the action for the future, in general. Okay, so x becomes 1, but by virtue of what did x become 1? Where did you look to know that x would become 1? Yes? We looked inside the function, in the state. So, and which instructions did we have to run to produce the result x is 1. X is x plus 1. And where did you find these instructions? In the body of the function, in the state, connected to the name of the function we call. So we actually took incorrect, we checked in the state, we took the body of the function, and we ran it. Yes? Sorry? Oh, but we should do this in a group, you know? It would be much cooler in a course. You're 100 people. We have to exercise on this. But anyway, so now this means that we just put the body of the function and we don't change the state. But where does the body of the function come from? From the state. So I'm going to say where, because I cannot just conjure it out of thin air. I have to say where does it come from? Where S of f. F is the name of the function. S of f was, well, the whole function. So that is unit goes into B. So let's look at the example above. And so with respect to the definition of a value we've given, what is inc x? Which of the letters is it? F, S, B? F. This is F. Great. Okay. Where's S? Sorry? The whole state. Which one? The first or the second? The first. Yes. So this is S. Where's B? So the body of the function, that would be? And this is the body of the function. Okay? Nice. So in our case, we found eval inc x. The state was x is 0. And inc x is, I'm going to write all of it out. And inc x is unit goes into x is x plus 1. And what does this become? No. Not x is 1. We don't change x in the state yet. Look at the rule above. We don't change the state when we call a function. We just change the code.
So it becomes unit.
No.
X equals x plus 1.
X becomes x plus 1. And what about the state? It doesn't change. So I'm just going to put 3 dots. Not yet, but now it's about to change. So we just put on our to-do, we change the program. We just put on our the program is our to-do list. We just put on our to-do list, and we have to run the body of the function. That's a significant change. If we change the body, or if we change the program, which we have changed, or we change the state, we've changed a lot. So we don't change two things at once. It would take too many steps. Also maybe because the function takes 50 steps to run. Maybe it takes 50 million steps to run. So we cannot just run it right away. That's the reason why we just say, okay, so you call a function, you want to perform an action. What do? We just check, okay, what is the action? We take the body of the action, we put it in the code, we're done.
Yeah.
We still have to do it, of course, but we're done for, at least we've set the action up. Then, of course, in a microsecond, eval will be run again by the CPU, so then we do it. We don't need to do everything at the same time. We're in a cycle. We are in an infinite cycle of operations. Now, this act of calling a function is called function call, invocation, execution, evaluation, even application, among others. So don't be surprised, these are all standard, widely accepted terms. So if you hear one of them, then it's fine. I might say myself, we call the function, we invoke the function, we apply the function. I find it very fancy actually to say that you apply a function. It's beautiful, it's methy, but that's life. Okay. Let us now take as an example the example of drawing a square. So, do you remember? Now, and of course, I know it seems like we have kind of an unhealthy obsession with drawing squares in this course. But the point is, we don't want to do very complex things. We want you to see the patterns. That's why we choose something simple. Otherwise, the pattern is complex, and the program we're writing is complex, and we have too much complexity at the same time. So this might slow down understanding. But, remember, how did we draw a square? We want to draw a square of n by n times n, asterisks. So what were the elements of the square? Do you remember?
Asterisks and lines.
First rows, the lines, the rows. Those are the elements. So now, I will say, okay, to write such a program, I will say, okay, first of all, n, we have to read it, that's int of input, okay, that's our usual reading of input. Then of course, the square is an empty string in the beginning. And then, I will state that drawing a square equates to drawing how many rows? N. Cool. So you know what? I is 1, while I is smaller than n, do row. Haven't defined the row yet, but in 1. So I just say row. And then I becomes I plus 1. That's a square. Of course, what am I missing? Row. Okay, cool. What is a row? People, what is a row? A bunch of asterisks, right? How many? N times. Okay, so I'm going to use another variable here. J is... Oh, wait a second. Let's start from 0. I is 0. My apologies. So J is 0. While J is smaller than N, do... No. It's not per se better. It's also not worse. Asterisk. So the row is n asterisks. And then, well, it's a row. So what do we need? Don't we need a new line? Otherwise, they are all stitched together. Yes? So, you know what? We need a new line. And I don't want to think about it yet. So I say new line. What do I miss now? Asterisk, a new line. Okay. Remember that we had variable s in the beginning. S is s plus asterisk. And what about new line? S is s plus backslash n. And at this point, we can simply say that drawing a square, well, we just say square. And there you go.
But isn't the program gonna stop if it doesn't see, for example, asterisk? Because it doesn't know what asterisk means yet. So it has to.
But why wouldn't it know what asterisk means yet?
It hasn't seen the asterisk.
But when are we going to call the function row? after we call square. So we define all the functions. We say what the actions are. We put them in the state, but we're not calling them yet.
So they're already defined.
So when we call them, that's the very last line. But at that point, they are all defined. It's a form of late binding. This is not entirely translatable into Python. So in Python you might... No, but actually Python should be able to do this.
But just to be sure, you
With the definition of functions. You can define them in whatever order typically. Yes?
I just don't get why it would run again if you aren't in a while loop. Because if
What?
you would say that it first runs the n is int, then the s, then the square, then the row, and then after that it gets defined. So yeah, but after those two are run, it's not gonna run again if it's not in another loop.
We draw only one square.
Oh,
use that.
So what happens here is that the first mention of square, that's the third instruction, it simply states what drawing a square does. It's not drawing a square. It's just saying drawing a square is I0 while I is smaller than n. So basically drawing the square is, you see a y, you see a row. So you could read this in your mind as a square is a bunch of rows. Okay? Because the y is intuitively a bunch of, and the row, yeah, it's a row. Okay? That's what drawing a square is, but we're not drawing it. We're just saying, we're writing the instruction manual, you know? How do you draw a square? That's how you draw a square. It doesn't mean that we are actually drawing. Then we say, okay, how do we draw a row? We can state how we draw a row, and it's a bunch of asterisks followed by a new line. Then we say, how do we draw an asterisk? We just put in S another asterisk. How do we draw a new line? We just put in S another new line. And now that the whole construction is ready, we press the red button. And we say, draw the square. But I need to do something to artistic, then he also had a question, sorry, and I will put here a red button. It's like the red nuclear button, you know?
Yeah.
Okay, so you had a question, and then you. Sorry? No, then he puts a new line after every asterisk. It's very ugly and you don't get a square, you get another figure. It still works in the sense that you get something out of it, but then the names do not match. And then, I mean, for the computer it doesn't matter, because you could also call all these functions A, B, C, D. But for us, that's the definition of it doesn't work, because the name of the function suggests, like he was seeing before, you know, the telepathic connection. You're setting up a telepathic connection, you say, this is going to draw a row, then you don't draw a row because you draw asterisk slash n, etc.
Draw a long line. A vertical line.
It draws a very long vertical line, yes. And?
If we define a new function and inside of it we invoke this function and multiply it with 3, let's say, will it draw 3 squares?
No.
And will it work in first place?
Wait a second, what would you like to do? So you could change n, and every time you put a square, it's going to draw the square again.
Yeah, I know, but if you find a new function and inside of it you invoke this function.
Oh, if you call it 3 times inside a function, it's going to draw 3 times the square.
Okay, and if you multiply it,
Yeah.
3, so square multiplied 3.
No, the square is not a value yet. So we cannot multiply it with anything. Now, I'm going to do a refactoring of this project, you know? So this was all in a file. But now I say, okay, you know what? Now I'm happy with this definition. So I put these two functions in a new file, and I give it a new name. I call it basics. And this is not Python, it's kind of a meta Python, so I call it mpy, meta Python. Okay, this is a file, and then I put the row in another file. I call it row.mpy. Okay, and now I put here the code for drawing a row. But of course, drawing a row requires the asterisk, so now I have to say somehow that the row needs to use the definitions from the basics file. So I add a line of code here that says import basics. It depends on the language. In the language I'm defining, no. We don't strictly need it. And so here, before we continue, otherwise we cannot call the row function, we do import row. But now, what's happened? Stop scrolling. Are you kidding me? Yes. Okay, and now this here becomes, let's say, main.metapy. So, main.metapy. And what's happened? Now, what do we need to know about basics? What do we care about in basics? Yes? So basics will remember for us what drawing an asterisk means and what drawing a new line means. Okay? So we forget, because we don't care about it anymore, basics will remember it for us, we forget what it meant to draw an asterisk. Notice that I'm not putting the cross on the names. We remember that we can draw asterisk and new line, but we forget how. We don't care. The name is good enough. What does asterisk draw? Most likely an asterisk. Okay? And what about row? Well, about row, we forget how the row is drawn. This is called abstraction. And abstraction, which means removal, what abstraction is doing, it makes it look simpler by removing what? Yes, but those basic functions, I mean, they are smaller.
I'm not sure.
They are small. Are they the fundamental piece of information about drawing a square? No. So they are details. They are elements. They are irrelevant details. So we forget the irrelevant details. Abstraction, and it removes between brackets irrelevant details. But is the name of the function row an irrelevant detail? No. We still need to remember that row exists, but is the fact that row initializes a variable j, is that relevant for drawing the square? No, because we just want a bunch of rows. How the rows are made, we don't care. That is the fundamental nature of abstraction. We chop details off. And we store it elsewhere, of course. The computer is good at remembering details, but we are not. We don't care. And so, what's happening now is that the program, if you look at the program to the left, what is a square? A bunch of rows, and that's it. Is that what the square is? Yes. And we trust, and we trust that the row is implemented correctly.
But if it isn't, you need them to...
The row? Then we need to fix it. Yes. easier. According to the semantics we defined, it's there, it's accessible.
Yeah, that makes sense.
In Python, this would be a slightly more complex story. But that's the reason why I'm explicitly saying this is meta Python. We'll see how to reach together. Okay? So now, of course, you could say, but suppose that we're doing a project and there's 3 people, and one person needs to build basics, one needs to build a row, and one needs to build mail. Okay? But one of them is a fun guy and he writes nonsensical code. Okay? He finds it funny. Now remember, whenever you write code, there is an adage about how you give names and how informative the names you give are. These names have to match the code. If someone says asterisk, but instead of drawing an asterisk, he draws a new line, it doesn't make sense, you know? And so the idea is that whenever you write code, you should give names in such a way as if to be as representative as possible. And what you have to imagine is that the code you write will be maintained by a psychopath with homicidal tendencies who knows where you live. So when you think, it would be funny to call the asterisk function new line, remember about the next maintainer of the code. Okay? So, do you want to take a break? Are you sure? Okay, now, the rest of the lecture is not going to be very heavy. Oh god, I saw it flicker, I thought, oh no, it disappeared. So it's not going to be very heavy. But now, I want to discuss the nature of actions in our intuition, because I'll go back to the drawing of the homomorphism, and I'm surprised that no one finds it a funny name. I do actually. Anyway, if I tell you to drive, get your car and drive, okay? What's your question? What would be your answer? I tell you to drive. What would you say? Oh, you can drive. Let's assume you can drive. You have drive. Can you drive? Fantastic. So I tell you to drive. What's your answer? What's your question? Where? Where? Yes. Okay. So, and it's not the same, you know, to go, I don't know, to Utrecht or to go to Molenbeek. Molenbeek, Brussels. Yes. Because you are in Brussels, of course. What are you thinking? Something racist. But anyway, but the point is, it's not the same because you get to a different place. But you drive, it's kind of the same action. The action is the same, but the outcome is different. So we need a way to translate this where to extra bit of information that changes the action into something that also is implemented in code. Now let's go back to our incrx. I want to define incrx, but incrementing x, just like drive, if I tell you increment x, what would be a reasonable question to ask? By how much? Right? It's kind of the same. And of course, at the end, x is incremented, but in a different way. And here's the reason why we put brackets in here. They were just a placeholder because between the brackets, we will put what are called the parameters. And separated by comma, let's begin with just one parameter. And then I say x is x plus k. Now, of course, x was, let's assume x was 1. And then I call incr x of 5 plus 1. What do you think is going to happen to k? What is the connection between k and 5 plus 1? Is there a connection, maybe? Yes, what's for connection?
So k will become, well, 5 plus 1 seems safer to me. You know, because we take it slow, you know? One step at a time. Who said it? One step at a time. And of course, that will become 6. So now, so I will just ask you now, so we can get it out of our system. What is the value of x here at the end of everything? It's going to be 7. And is incr x going to change? No. So actually, I'm not going to say anything about incr x. Still there. Dots. Okay? Cool. But so, to run this, of course, when we get here, when we are running x is x plus k, what do we expect k is going to be? Which one? Which integer? No, k. What is k going to be? 6. So k is going to be 6. Now, a bit of terminology. Now, this here, so these brackets, they contain what we call the parameters. And the value, the expressions that we want to bind to the parameters are called arguments. Arguments. Let's discuss the semantics then of function invocation with parameters. Now, we have eval, and eval is the call of a function with a bunch of arguments. And it doesn't matter how many arguments we have. So I'm going to say a1, comma, a2, comma, whatever. A bunch of arguments. And we have the state. And now, the first thing we do is we look something up in the state. What do we need to know? What do we need to extract from the state? So, the function, and the value of the arguments we have it, it's a1, a2, etc. But we need to extract the function, the body of the function, yes, but also what else do we need to know about the function? So, okay, I extract the function, and what do I get here? We get the angle brackets, and we get the body, but to the left of the arrow, what are we going to find? And that is now very meaningful information, yes? The parameters, yes, and they have names, p1, etc. Now let's use the same representation. So p1, p2, etc. Okay? And these things here, they will be variable names. They will be variable names, whereas these things here, what will they be? Expressions. It's even bigger than values. Like, values would be 3, 4, 5, but 5 plus 1 is not a value, but it's an expression. Okay. And so, how are we? What are we going to get out of it? Now, I will tell you right away, the state does not change. And of course, eventually, we will have to run the body. But before we run the body, we need to take care of some preliminaries. If you look at the body above, in the example, then we do x is x plus k. So what do we need to prepare in order to be able to meaningfully say x is x plus k? The x we have already. The x is 1. We need to fill in the k. With what? And what is the argument? No? 5 plus 1. So, and underneath, in the general case, we need to connect the parameters with their arguments. How do we connect them? We want to connect them. We want to tie them together. I'm looking for a specific word here. Well, yes, that was the word. We want to bind them together. How do we bind them? How shall I bind them? I have P1 and I want to bind it to A1. What do I put between them? Column equal. Yes. Pi is bound to A1. Pi1 is bound to A1. And P2 will be bound to A2. And so on. So, going back to the example above, we encounter eval of incr x of 5 plus 1, and the state will contain x, which is 1, and incr x, which is a function k goes into x is x plus k. And what happens now? Let's connect the letters. Where's F in my example? Which one is F? Incr x. Yes. So this was F. Which are the arguments? 5 plus 1. So this is A1, right? What are the parameters? Sorry? K. K is P1. Where's the body B? This is the body B. And now it's just... So now we have to write this, the thing I just underlined. But instead of P1, A1, etc., I just put the things I know. Oh, and by the way, this is kind of a stupid question now, but what is this? S. So, what is the result then? So the first bit is P1 is bound to A1. So what is that? K is 5 plus 1. I have no more arguments, so I'm done. If we had more arguments, they would be here. And after the argument, what do we put? Sorry? No, not yet. Look above. The body. There's a B. After P1 is A1, P2 is A2 above, and then B. Now we have to do B, right? And what is B? X is X plus K. And is this risky business now? No, because K will be 6. Because we initialized it correctly. Now K becomes 6. And the state? Well, the state doesn't change. And that's it. So I set up in the rest of the program that we have to initialize K with 5 plus 1. And then we run the body. Yes?
Can we pass a function as an argument?
Whoa, Tiger, easy there. Slow down. We are going to do that. Do you have any questions? No? Sorry? For the what? Oh, after the lecture, yes. Then I thank you very much, and until next time.